there was a speaker that came in. I think it was the first speaker that came in. His name was Andrew Walker, and he, like, in the middle of his presentation, he talked about a piece of writing by Neil Stephenson called, like, In the Beginning or something like that, or Command Line. I'm not sure which one he was talking about, but that rung a bell in my life because this book here that he wrote was one that had a, like, tremendous influence on my life. I read it, like, in the beginning of, like, college, like second year or something like that, and it stopped my habit of reading for pleasure, because it was so pleasurable that when I started another book, it just killed my motivation because I'm like, this is not good in comparison to what I was reading with this guy here. So then I just, like, kind of stopped reading after this, right? And then there was a sequel, and then also, I'm sorry, no, a prequel, and then a pre-prequel, and a pre-pre-prequel that were, like, planned. And I was sitting there, like, so excited about when it was going to come out. I think I waited 2 or 3 years, and then finally it came out, and it was total, like, it wasn't good, right? So I think, like, if you take that feeling of people who are, like, in love with Star Wars, and then you maybe multiply that by 10, and then when the first prequel came out, like, that feeling, I think that was, like, I think that kind of described how I felt when the prequel to this book came out. So anyways, the main one of the main storylines or the threads in this book is about encryption. And so our extra credit assignment is going to deal with encryption. Okay. So the first so right now you guys know about blockchain, right? And so, like, blockchain is how they put together the cryptocurrencies and make sure that the encryption on them are valid, I believe. I'm not too sure how blockchain works, but Will does, right? You can probably ask him about it. But then before blockchain, there were public and private keys, right? So the way that this works is you have a public key, and with that public key, you can encrypt the message. And then with a private key, the person who wants to read that message is able to decrypt and read, right? And this involves extremely large primary numbers, which are hard to computationally hard to compute, right? So then the public key would be this huge what's it called, prime number, and then the private key would be a huge prime number, and that would ensure that the message that's encrypted has a certain level of security, because in order to break the cipher, you would need to generate, like, every possible prime number, like, up to the one that is used as the public and private key. And then, mathematically speaking, that would take, like, at the current state, it would take, like, the longer than the age of the universe to do. So this is, like, the state of encryption as it is now, right? And I don't think that's going to change until, like, quantum computing comes into the mix, and then everyone's secrets will be aired out, right? So, but next, right? Like, when you first start out, what is the most basic cipher? The most basic cipher is called the Caesar cipher, right? Where you take the alphabet and then you shift it over. Right. So if I shift it over, then that means every time in my encrypted code I write B, what I'm actually doing is I'm trying to write E. And when I write C, what I'm trying to do is write F. Right. And so you can have 26 different, or I guess 25 different permutations of the Caesar cipher. Right. And if security is not that big of an issue, then this would be the way that you go. Right. Very easy to unencrypt. And then another level of sophistication would be the substitution cipher. And the substitution cipher is where the matchup, right, from the letters of the alphabet to their encoded letters of the alphabet are not, like, in order, right? So it's not like A, B, C, D, E, F, G, and you just shift it. It's the B is, some letter of the alphabet, the L is some letter of the alphabet, the H is some letter of the alphabet, right? So this one's a little bit more sophisticated. And this was actually the cipher that was used during World War II, right? Or at least a version of it, to send messages via the radio, and because of the encryption that was used, Germany was able to basically act with impunity, right? Where they had their fleet of U-boats and they were able to sink every ship that was crossing. Well, not every ship, but the substantial number of ships that were sending supplies from the Atlantic, over the Atlantic, from the U.S. to Europe, and thus winning the war, right? And so we were on our way to a new world order with, Nazi Germany at the head of it, until Alan Turing and his team deciphered the cipher that the Germans were using, and they were using a sophisticated version of the substitution cipher, right? And what they were doing is they made a machine. The Germans did. Looked something like this. Had a lot of rotors and motors, right? And it had different configurations, right? And so the Germans were or the captain of each boat were given one of these machines. They were given a book with 365 pages in it. Every page in the book corresponded with each day's settings on the machine here. And by doing this, they were able to communicate with security during the war, right? And it wasn't until this was broken that the U.S. began to push back, and eventually, we are where we are, right? So you can kind of say, like, computer scientists saved the world, basically, right? The world as we know it. So what is our extra credit assignment? It is to code the Caesar cipher, right? So you're going to give it text that's encrypted using the Caesar cipher, and then it will output the unencrypted text, or the decrypted text. This shouldn't be that big of an issue, right? And like, this is the way I have it set up, where it's like you'll get 1 percentage point for doing the Caesar cipher, 1 extra credit point or percentage point added to your grade for completing the substitution cipher, right? So here's the substitution cipher, where it's like randomly generated, where of course like A is not encrypted to A and B is not encrypted to B, and so on, right? But you're just like randomly given a random letter. So encrypting is not that big of an issue here, right? I mean, you guys should all be able to put that together. But then the decrypting is kind of an issue, right? So how would you be able to create code to decrypt this substitution cipher? Well, if you gave this to somebody in charge of security, they would say that this is a very weak cipher. And why is it weak? Because you can attack it, or find a way to solve this by using a frequency analysis, right? So you have all the letters of the alphabet, and then every letter has a corresponding percentage, like, of use, right? So you have like E is the most commonly used letter in the alphabet, so like say that's 22%, right? And then we have A is the next commonly used letter in the alphabet, that's like 18%, right? And so on. And Z probably has like a 0.05% percentage of use, right? So then to break a substitution cipher, or a message that is encrypted using a substitution cipher, as long as you have enough encrypted texts, you can break it using frequency analysis, where you take them all, taking all the letters, count how many each one was used, assign it a percentage, and then the most commonly used letter would most likely be the E, right? And the next most commonly used letter would probably be the A, and so on. And then you would substitute the letters in, output the text. Of course, it might be off by a bit, but from there, the secondary, like the fixing, like polishing it up, is not that big of an issue. So that's how you would encrypt the substitution cipher, and that's how you would decrypt the substitution cipher, right? So that's another extra credit point, or another percentage point. And then the last percentage point is you encrypting the encryption process of the Enigma. So you'd have to do research on this. You have to figure out, what is this? And well, it's composed of a plug board. Yeah, we don't need to know about that. A light board that affects the encryption process. 5 rotors. Each 5 reflect the number of substitution ciphers that are used. So those are all relevant. And then there's a reflector. I'm not sure if if that is relevant, but it might be. And so you'll study it and then figure out how it works, and then you would encode it. You would code it, right? And then you would essentially end up with an application that's something like this, right? Where I could set the settings to A, B, C, and D, put in my encrypted text, and I could encrypt it, right? And then I could decrypt it. Okay. So then this last one is a bit of a challenge, and that's how you would earn 3 percentage points added to your final grade.